What if the solution to global warming and the energy crisis wasn't buried deep underground or soaring high on manufactured satellites, but swaying gently right in our backyard? We spend billions trying to engineer materials that can mimic nature's efficiency, yet we often overlook the perfect systems that have been iterating for millions of years. Take the sunflower. It's an iconic symbol of summer, a powerhouse of oil and seeds, and, crucially, a flawless biological solar tracker. But could we move beyond appreciating its beauty and actually plug into its potential? Imagine fields of gold that do more than just grow food. What if these agricultural landscapes could also be our living power plants, generating decentralized, carbon-neutral energy? This isn't a sci-fi fantasy. This is the foundation of the helianthovoltaic hypothesis, a fascinating thought experiment that asks if we can transform the sunflower into an organic, hyper-efficient solar cell. Let us explore the intersection of botany and electrical engineering. Let us look deep into the anatomy of the sunflower and determine if it possesses the key to unlock truly sustainable green power. The first and most compelling piece of evidence in favor of the sunflower is movement. It's called heliotropism. From the moment the young plant sprouts until the flower head matures, it follows the sun across the sky with uncanny precision. In the morning, the flower faces east, soaking up those critical early photons. It slowly pivots to the west throughout the day, maximizing its surface area exposure to the most intense sunlight. At night, it resets, awaiting dawn. This seemingly simple biological trait addresses one of the most persistent weaknesses of conventional solar technology. Traditional photovoltaic panels, the large blue or black rectangles we see on rooftops, are static. If the sun is directly overhead, they are performing optimally. But once the sun begins to angle, their efficiency drops sharply. To combat this, solar farms often install expensive, high-maintenance mechanical tracking systems. These trackers consume energy, require heavy lubrication, and inevitably break down. A sunflower, however, tracks the sun organically, utilizing hydraulic pressure and hormonal signals in the stem. It's a biomechanical tracker operating on its own internal energy budget, essentially at zero external cost. Studies tracking the efficiency of solar panels mounted on artificial trackers versus static panels show a significant boost, often ranging from 25 to 40% more energy generated per day. If a natural system can achieve this tracking without complex machinery, the potential efficiency gains for a helianthovoltaic farm are staggering. Now, simply tracking the sun is only half the battle. How do we get the electricity out of the flower itself? To answer that, we must dive into the fascinating world of organic photovoltaics, or OPVs. We are not talking about magically turning a plant into a battery overnight. We are talking about utilizing the plant's biological components and structures as the framework for energy conversion. Plants already specialize in energy conversion. This process is called photosynthesis, where light energy is converted into chemical energy sugars. The chloroplasts within the leaves and petals are miniature biochemical factories using pigments like chlorophyll to capture light. The key scientific leap here involves replacing the silicon in traditional solar cells with organic compounds derived or inspired by the plant itself. Researchers are actively developing desensitized solar cells, which utilize natural pigments, not unlike those found in flowers, to absorb light and create an excitonic reaction that generates a current. The sunflower's structure provides unique advantages here. The iconic head of the sunflower is not a single flower, but a complex collection of thousands of tiny florets arranged in a highly ordered Fibonacci spiral. This spiral maximizes packing density and ensures that every single unit is exposed to light optimally. Imagine synthesizing a thin layer of highly conductive biological material, perhaps utilizing graphene oxide integrated into specialized leaves, or developing dyes from the petals, rich xanthophyll and carotenoid pigments. These could act as the photoactive layer. The plant wouldn't be generating electricity through its normal photosynthesis, but its biomass would become the structural and chemical substrate for electricity generation. The plant essentially grows its own power grid, replacing the need for expensive, mined silicon and highly polluting manufacturing processes with clean, biodegradable organic compounds. The whole plant becomes a living, growing, self-assembling solar collector. This vision is seductive, but the transition from hypothesis to reality faces massive engineering and logistical hurdles. The challenges fall into three main categories: energy density, harvesting methods, and scalability. Let's start with energy density. Conventional silicon solar panels are highly efficient, converting between 18 and 22% of incident light into usable electricity. Existing organic photovoltaics lag far behind, often stuck in the single-digit efficiency range, although that is rapidly improving. Even with the tracking advantage of the sunflower, the total energy harvested per square meter of agricultural land would be significantly lower than that of a high-efficiency solar farm. We would need vast fields of sunflowers to generate the power equivalent of a smaller, centralized photovoltaic array. This raises the thorny issue of land use. Is it better to dedicate land to high-yield food production or lower-yield energy production? The second critical challenge is energy harvesting. If the sunflower is our solar cell, how do we plug into it without killing it? If we are treating the plant as a continuously growing energy source, we must find a way to extract the electrical current efficiently. One conceptual approach involves harvesting the plant at the end of its life cycle. Once the flower head matures and dies, the organic solar structure be harvested, processed, and the energy storage materials recycled. This creates a system that combines bioenergy burning the biomass for heat with OPV harvesting, but it doesn't solve the continuous power demand problem. A far more futuristic idea is non-invasive extraction. Could the plant naturally shunt its excess energy into a biological capacitor or storage unit located in the root system? Researchers are investigating bioelectrochemical systems that could use microbial fuel cells in the soil to react with root secretions and generate small currents. If the sunflower could be genetically engineered to produce highly conductive sap or store charge in its stem walls, we might be able to tap the electrical potential using external electrodes without damaging the plant's growth mechanisms. This is science far ahead of our current capabilities, but it points to the potential of synthetic biology integration. Finally, we face the issue of scalability and infrastructure. Renewable energy must be robust. A traditional solar farm is built to last 25 to 30 years with minimal maintenance. A sunflower field, however, is a seasonal crop. It requires planting, watering, pest control, and harvesting every year. This means the energy output is tied inextricably to the agricultural cycle, introducing seasonality and climate vulnerability into our energy grid. A drought, a pest infestation, or poor soil quality could simultaneously wipe out both our food source and our power source. Despite these formidable challenges, the helianthovoltaic concept opens up profoundly interesting avenues for thinking about the future of energy. It forces us to move beyond the traditional dichotomy between agriculture and industry. Imagine a world where our energy infrastructure is not composed of cold steel and mined materials, but is a vibrant, living ecosystem. This integrated approach, often termed agrovoltaics, typically involves planting crops beneath static solar panels. But the sunflower hypothesis reverses this. Here, the crop is the panel. This system would offer incredible decentralization. Power could be generated right where food is grown, dramatically reducing transmission losses and empowering local communities. It champions circular economies, where the end-of-life solar material simply composted back into the soil that grew it. The sunflower reminds us that nature has already solved most of our toughest engineering problems with an elegance and efficiency we struggle to match. The question is no longer whether we can generate electricity from plants, but how quickly we can learn to cooperate with them. Perhaps the future of sustainable energy won't be found in the next breakthrough in crystalline silicon, but rather in perfecting the art of turning a simple, beautiful, sun-following bloom into a quiet, clean, living power station. It's a vision where our energy grid is literally alive and breathing, swaying gently in the wind, always watching the sun.